Okay, let's just do some science papers. This question comes from the 2021 exam paper from OCR Gateway. This one in particular is paper 5, physics. And the question was on the higher and foundation paper. They looked exactly the same. So this full question is in the description. Open it up. I suggest you do this before the video actually starts, using your brain, and that's how you learn. But anyway, part A is here. Let's read it out. Then here are some events in atomic theory. And then we have a table there with the names of some scientists and their discoveries or theories. Part 1 then place the events in the order that they occurred. Write the numbers in the boxes below. One has been done for you. So we can see that these 5 events here all took place between 1897 and 1932. If we read through them, Thomson discovered the electron, published findings in a scientific journal. Chadwick discovered the neutron, but this one's been given to us already, number 2, down at the bottom. Bohr suggested electron shells after a science conference. Rutherford did experiments showing the atom had a nucleus. And finally Thomson published the plum pudding model in a scientific journal. Okay, try the question yourself. Do it now. I'll wait. You can pause me. I'll wait. So, what is an atom? Here's some events in atomic theory. Well, atom, the word atom comes from a Greek word atomos, meaning indivisible, or can't be broken up into smaller pieces. What do we mean by that? So, imagine a leaf. Here's a really bad leaf, but imagine, let's say. And what we're going to do is we're going to cut it up and divide it. Then take a smaller piece and then use this piece to do the same thing again. So we can divide it, we can cut it up into a smaller piece, and then use that piece to do the same thing again. Okay. Now, you might think that at some point this process would end, but imagine if there was some end, if there was some final piece that you could get to and you couldn't break it up anymore. That's what the idea behind the atom is. And before 1897, our idea behind the atom was that they were small, hard balls that couldn't be broken up. That couldn't be broken up. But all this changed in 1897. We start off with this experiment. You take a glass tube and you suck all of the air out of it to make a vacuum. In reality, there's always going to be some amount of air left in the tube, but let's pretend there's absolutely nothing inside that glass tube. You can then take some metal plates. Here I've drawn them as cylinders. Okay, you can put them in the tube, and if you connect a battery or another source of electrical power with very high voltage, you can charge up the plate. We use the word anode and cathode to denote which ones are positively and negatively charged. And you can see that the anode there has a small hole in it, which is going to be important. Now this setup right here is called a Geissler tube. It was very famous. All of the physicists at the time, around late 1800s, were trying to explain what happened afterwards. A ray of light would appear, okay? And because it came from the cathode, it was called a cathode ray. And people were trying to explain this. And now it's not hard to actually make. We can see a few different videos of these in real life on YouTube. Here's a few. Okay, so in a laboratory they're pretty easy to produce if you have the right equipment. You can see some purple ones and some green ones. But also you can make these at home. It's not too difficult. And if you look at what these people at home do with a magnet, you can see that they can bend the cathode ray with a magnet. And they knew this too at the time. So if you had a positively charged object, the cathode ray would bend or deflect towards the positively charged object. Okay, so you could attract it. And if you brought in a negatively charged object, it would repel the beam. Okay, push it away. So this is all quite interesting. Now the only way this makes sense is if the beam itself is positive or negative. Interacting with positive and negative things, it has to be positive and negative. And we know that like charges repel each other, and unlike charges attract each other. So the cathode ray has to be negatively charged. Okay, you should have filled in the blank on that one. It also didn't matter what metal was used. Okay, you could use iron, you could use copper, you could use aluminium. It didn't matter. It seemed to work with anything that you could pass electricity through. One of the most prominent physicists at the time, J.J. Thomson, laid out a theory that the beam of light, the cathode ray, wasn't actually a beam of light at all, but it was actually made of particles. His work showed that these particles would have to have a negative charge. They would have to be smaller than an atom because they were so easy to bend using charged objects. And also, it would have to come from any atom. That's what they saw. And this new theoretical particle was called an electron. And so this was the first big breakthrough. What J.J. Thomson saw when he saw atoms as being those small hard spheres, but the electrons as being some sort of smaller thing that was coming out of them. And so as you turned up the voltage with the battery, the electrons would be ripped out of the atom. And that's where the cathode ray was coming from. This also explained really clearly why the ray was bending towards positively charged objects. They were just attracting the electrons. Also, a negatively charged object would push the electrons away. Very good. So this theory of the electron existing made sense with the reality of people seeing the cathode ray. So a huge step in atomic history can be filled in now. I'm going to put number 1 right there. Thomson discovered the electron, and he then published his findings in a scientific journal. So what does that mean? So J.J. Thomson didn't come up with everything by himself, right? He had a team of people, and many other teams in the world were looking at this cathode ray experiment and trying to figure it out. He first shared his idea or theory of the electron with the people he worked with, and then he would have shown it to other people who were experts in the field, and they would have come back to him with suggestions where he could improve or if he did anything wrong, and we call that peer review. Like in your school, your peers are the other students, so his peers would be people working on the atom. Then when Thomson is happy with everything and it's been checked by multiple people, he can publish it. What that means is he's basically putting it out into the world for other scientists to find. And they can use it, maybe to form their own theories, or maybe to check Thomson's work. But that's how science works. If we slowly build on other people's ideas, and it's this kind of continuous growth of knowledge. Okay, so the huge shock to all of this that has kind of gone over our heads, and something that a lot of people disagreed with, was Thomson was basically saying that the atom was now divisible. You could break it up. But the whole idea behind the atom was it was this thing that couldn't be broken up. So now they had to explain what an atom actually looked like. And Thomson spent around 7 years responding to the trolls. So to J.J. Thomson, the electrons all repel each other. They push each other away because they've all got a negative charge, so they push each other away. So the only way they can exist is if there's some sort of soup or dough that's a positive charge that surrounds the electrons and stops them from flying away. It holds them in place. Now, the plum pudding model is probably an outdated term. Here's a plum pudding for reference. But I'd probably call it the chocolate chip model of the atom. Anyway, we can fill in the next part of the question. So, Thomson discovered the electron, and then to explain where the electron was coming from, he said that the atom looked like a plum pudding. And this was the theory he put out into the world. Shockingly though, people did not believe him. They thought he was wrong. They thought, you cannot seriously still believe that the atom is divisible, can you? But he was right. So now we're going to look at a completely different experiment. This experiment was done first by Geiger and Martin. And what we have is we have a small box of something radioactive, because we like playing with that, and it emits alpha particles. We don't really care what an alpha particle is right now, just that it's something small that has a positive charge. We fire it at a thin gold foil. The reason it's gold is because you can spread gold really thin. I think a bar of gold can be spread, if you spread it thin, it covers a tennis court, right? Really thin. Then after it goes through the gold foil, we want to know where it lands. So we have a big screen around us to detect where the alpha particle actually ends up going. So if you run the experiment, you can see that the alpha particle will pass straight through the gold foil. And you can see it on the detector there with the orange X's. Sometimes it got a little bit deflected. It got deflected quite a bit actually. It was a bit strange. They thought it shouldn't be deflecting that much. But really surprisingly, about 1 in every 7,000 times the alpha particle would bounce straight back off of the gold foil. And there was another young scientist at the time who had been a student of J.J. Thomson's and now worked with him. He thought this experiment could explain something about the atom. He thought it could actually disprove J.J. Thomson's plum pudding model. So he did this experiment loads of times with different equipment and different places to make sure it wasn't a fluke. But no, really, the alpha particle was hitting the gold foil and bouncing back. It just didn't make sense. Rutherford said that it was as if a bomb landed on a piece of toilet paper and bounced straight back into the sky. Why was it bouncing back? Well, in Rutherford's mind, the plum pudding model couldn't explain why it bounced back. In the plum pudding model, all that charge is spread out thin. And so the charge is never strong enough to repel the positive alpha particle. It should just fly straight through. Rutherford said that if all of the positive charge was actually concentrated in a ball, then it would have enough power, it would have a strong enough charge to deflect the alpha particle. So, maybe also the positive charge isn't actually a dough or a soup, but it's actually made of particles like the electron, but positive. And those were called protons. So if we run that experiment and we take a closer look, and if we could see the atoms, the plum pudding model cannot account for the fact that alpha particles bounce back. In Rutherford's new model, this explains why the alpha particle passes through most of the time, but very rarely the alpha particle flies, hits the center, the nucleus of the atom, and bounces straight back. Okay. So, what we've learned here is that Rutherford saw an experiment that didn't match up with the theory, and he updated the theory to match what he saw in the experiment. That's how science works. So the next piece of the puzzle is now available. The next thing to happen in atomic theory when Rutherford came along, he did experiments to show that the atom had a nucleus. Okay, you can technically finish the question here now, but we should probably talk about Bohr. He was also a student of both Rutherford and Thomson, and he was really keen to kind of prove himself, and he wanted to explain what the electrons are doing, because right now it doesn't make sense in Rutherford's model. The electrons are negative, the protons are positive, so they should be attracting each other. The electrons should be attracted to the nucleus. So a lot of people thought that the electrons must be going around the nucleus instead of going into it, but that didn't make sense either. They should still be falling into the nucleus, but they weren't. Things exist, and atoms aren't that small. So what was happening? Niels Bohr brilliantly used mathematics to show that electrons have preferred energy levels. or shells. What that means is that they fill these shells in a specific order. 2 electrons begin in the first shell, and as you add more electrons, they must go in the next shell, where you can fit a whole 8 of them. And if you want to add any more electrons, you need to go to another shell. They have to. This is what they have to do. They have to fill up outward. 2 can go in the front shell, 8 can go in the next shell, and 8 can go in the next shell, etc. Now, there's still one big question left to answer, and that is, what's going on in the nucleus? So this big piece of dough in the center doesn't make sense. The protons are all positive. They should be pushing each other away. Why are they not pushing each other away? And it wasn't until 1932 that a guy called James Chadwick showed that there had to be another particle in the nucleus. You can see them there in green. And he showed that this particle existed, called the neutron, and it had no charge on it, not positive or negative. And what it did was, it added padding to the protons, so that they weren't so close to each other and didn't repel each other as much, so that the nucleus could stay nice and stable and compact in the center. So that marks the final part of question 1. We know that after Rutherford, Bohr came up with what the electrons were doing, and 2 we got for free. Chadwick discovered the neutron. Okay, part 2 of the question looked like this. These events were peer-reviewed and communicated to others. Suggest why both are important in science. Right. Give that a go by yourself. Try and remember what peer review and communication would mean for science to work. Okay, so these 2 things are a big part of the scientific method, basically how science works. And I'm going to give a simple version here. We always start by looking at what we already know, all the science that's already out there, and then we come up with a question. Is this always true? What happens if you do this? In this case, people were questioning, what did we know about the atom? Is the atom actually indivisible? Is the atom actually a plum pudding model? What are the electrons doing in our current model of the atom? These kind of questions. So you come up with an experiment then to try and test the question and prove or disprove your idea. You get some results and you think about what they mean. You analyze them and you come up with an explanation to answer the original question you had. And then before you share your work, before you go and tell people about everything you've just discovered, you need to go through something called peer review. You need to share your work with your peers. After that, after your work has been checked and people have made suggestions and you've checked any errors you could have made, then you can publish your results, which would be communication. So people can learn from what you did, check it, do the experiment themselves, or even come up with a new question about the idea you had. So pause now, improve the answer that you just made, and then I'll show you how I would try and answer it. Okay, if I had this question in front of me and I was to just do it, why is peer review important in science? Well, when I do an experiment and I get some results and I come up with some sort of explanation of those results, I also want to get another opinion. Okay, maybe I'm wrong, maybe I made a mistake. Maybe the piece of equipment I was using was broken, it hadn't been for weeks and nobody told me. So they might need to check for mistakes. Or maybe, or most of the time, it's actually to get some advice. Okay? You want to get a lot of people's opinions on what you've just seen in the experiment. You don't want to just go with one. In terms of communication, why would I want to share my idea afterward? Well, a very selfish one, but a correct one, would be to get credit. If I discover something in science, or if I come up with a new idea and it actually turns out to be true, I want to have some credit for it. Maybe it's so that people could do their own experiments. And as you can see in the cycle here, the point of science is always to feed back into everything we already know, trying to improve our understanding of the world, to improve knowledge. And one final one, unless scientists communicate their work and what they discover and what they find to be true, we can't make technology with it. You know, people who make things need to understand how they work from the scientists first, so to help with a new technology.